Hello, it's Eugen. With this video, I begin short series of the movies dedicated to electroshock devices, also known as conducted energy devices or electrocution weapons or stun guns, etc. You know what I'm talking about. I plan to do it in 3 parts. In the first one, we should explore what these devices are and what requirements should they meet. In the second part, we will discuss the construction of the really available stun guns on market, how they are arranged. And in the last part, I plan to construct the stunner of my own scheme, maybe with the help of some commercially available circuits. Okay, today we should examine the stunners, what they are, and we will talk about their parameters. Let's go on. Let's begin with literature. While creating this video, I used the following sources. First two is Russian literature. This is the standard or GOST, as we say in Russia, about electroshocking device. It contains all definitions, conditions of testing of shockers, their main classes, etc. This book describes all the history of electroshocking weapons, how they are arranged, and some demands to mass-produced shockers. This is the beautiful white paper of Spencer Turner. It is in free access in internet. All these sources are in free access, so everybody can find it and read. So this is one of the best compendium of some scientific experiments about how electricity influences on human's body. I don't hesitate then inventors of the first others used this source. The fourth is some funny paper about experiment with electric eel and how it attacks people. Very funny and interesting paper. For example, it describes that when the eel attacks human, I didn't know it, it leaps from the water, and the height of this leap hits greatly the consequences, because some electric circuit forms with some characteristics which depend on this height of this leap. Okay, here is some two papers about reviews, medical reviews on influence of electric current to human. This is Russian forum, which contains concentrated information about electroshocking devices and their parameters. This is very useful document about comparative analysis of two types of shockers, taser and stinger, and the most useful in it is its appendix, when where the creators of stingers argue about the criticism of their device, and they describe some medical aspects of how it how it shocks the human. And the last one is international standard about effect of current of human being, very useful. Okay, let's begin with definition. What is in fact electroshock device? We all know that it is a weapon or equipment which makes something like this. In other words, it must render the enemy incapacitated or unconscious for a time of maybe several tenths of seconds to let the victim put itself to the safe distance from the aggressor. Okay. Also, what demands? It must be compact and portable, so we can bring it in our bag or pocket. Otherwise there is another flip side of this coin when some constructors try to minimize the dimensions of electroshock and put it, for example, in a lipstick form even. It is more dangerous for its user than the aggressor. We will talk about it in the next part, because the fingers of holding person is too close to the electrodes of the device in this case. Okay. Also, our electroshock must be safe for the object and subject of its application, because we must protect ourselves, but we must not kill the person who is dangerous for us, because we don't be in a jail. Okay. And it also should have a psychological effect, because in many cases we don't want to bring situation to physiological collision, and when the aggressor sees some sparks or loud noise, it may stop its aggression without any consequences. For example, it is true for wild animals. Dogs are very afraid of electroshockers. Okay, what's next? This is a table from the Russian standard, which I talked about in literature section. And it sets some important parameters of electroshockers. For example, in this cell, you can see classification of shockers for their output power, mean output power. And you may also know that it is measured under the load of 1 kilo ohm. 1 kilo ohm is standard resistance of the human's body under its clothes and skin. You can see that maximum output power is limited by, for civilian shockers, is limited by 3 watts only, not much. And this cell contains some values of output voltages of our stunners. It stretches from 12 kilovolts to 90 kilovolts. You can see that it is well enough to break down all protective layers above our body, for example, air, clothes, skin, and firm rupture is achieved under the voltages of from, for example, 30 to 50 kilovolts, as it is known from literature. It is well enough. Also, you can conclude that all the values which we may find in, for example, Chinese marketplaces like AliExpress, where we can find devices with output voltages of 1 million volt, for example, we don't need such voltages, and they are mostly fake. And these graphs contain classification of shockers under the types and groups and classes, etc. It is not very important information for us.
And what acting or mean currents should we have, and what currents are permissible for human, for not to kill him? This is the citation from another Russian ghost. You can see in this table permissible time of acting current from 0.1 second, 1/10 of second, to infinite. The second line indicates the current itself, and the third line is voltage. You can see that under 1/10 of second, human may resist to half of ampere current, according to this ghost, according to this standard. And under more realistic longitudes of, for example, 1 second, it's only 50 milliamperes. And according values of voltage is in the third line, we can see that 500 volts is enough to ensure half of ampere. It's you can see that it's greatly equates to 1 kilo ohm resistance of human's body. Okay, but we know that not voltage kills human, but the current kills.
This is a table and a picture of with a range of current acting on human's body. You can see that in the range of unity of milliamperes, human begins to feel current. It is so-called sensation or touch current, and its value is suggested to be 1 milliampere. Then while current increases, the pain increases. Some seizures take place, convulsions, and in a range of about 50 milliamperes, there is so-called let go threshold. It means that human cannot disconnect him from the part, current containing part, in such level of currents. Then in a range of 50 milliamperes to 100 milliamperes, fibrillation takes place. It's chaotic heart-muscle contraction, and more than 100 milliamperes, death takes place. All this, of course, depends on place of application of our electrodes and the range, the distance which current runs through our body. The worst case considered to be from the left shoulder to the right leg. It means that very long distance, and during this distance current runs through the heart. So that is the worst case. Let us examine in more details what is the object of application of our shocker. I drew such a picture, schematic. This is our electroshocking device, and if we don't apply it to nudist, the object has some clothes. It may be upper clothes, underwear. There is always air in the pores of the clothes or between the clothes and skin. Then skin goes. It is also layered structure with strong dielectric properties, especially on its upper layers, and our target place inner tissues of the body. So we have such a complicated layered structure of different heterogeneous materials. What should we do with this? We should know that all these materials, even inside the body,
have various ranges of resistance. You can see that the most resistance are bones, some hundreds of ohms on centimeter, and the most conductive is blood. It's obvious because it is a solution of salt in water, in fact. Okay, in the right picture we can see that it's a volt-ampere characteristic of air during spark breakdown. You can see that the magnitude of its resistance changes in order of dozens of order of magnitude of dozen units. So we obtain not only the big variety of resistance, but these resistances are not constant in time. The first conclusion from this is that if we want to test our shocker in a proper way, as some laboratories make, we should do something like this to break down some dielectric materials, but not to apply our electrodes directly to meat, as some people do. Okay, so to access the damaging current to the tissues of the body, a breakdown of several layers of dielectric is necessary, which is provided when a voltage of several tens of kilovolts is applied. And the purpose of this voltage is to achieve some maybe units of or tens of milliamperes, as we saw from the previous picture. Since the object of application of electroshocking our unit is characterized by non-stationary conductivity, with a change in its magnitude by many orders of magnitude during exposure, the effect of high voltage also cannot be stationary. Why is it so? Let us imagine this is also volt-ampere characteristics of spark discharge. We work in this range, arc discharge takes place, and if we remind Ohm's law, current is voltage divided by resistance. For example, we take 50 kilovolts divided by 1 kilo ohm and we obtain 50 amperes. It's too much, we will kill our human with such current if it is obtained in a constant way. Okay, and what should we do? For example, in this picture you can see that example of device which realizes this these voltages and current in a constant way. It is so-called Yakov's ladder, and you can see that it is such a big device. You may saw it in amusement parks, and it is powered by as minimum microwave oven transformer of maybe kilowatt power. So you cannot put this thing into your pocket. Yes. Thus, for reasons of portability and safety, the output signal of our electroshock should look like a sequence of pulses with a low duty cycle. It is a very important conclusion. What can be the frequency of these pulses? This is three pictures with the same thought in them. They show the curves of currents independence of the frequency. Curve 1 and curve 2 is sensation current and let go current with frequency. You can see that has its minimum in a range of 10 Hz to 1 kHz. And this is the another pictures, and from the Turner's investigations, which I talked in the literature section. And they show the same, that the optimal range of currents is frequencies is about from from tenths to some hundreds of hertz. The another reason why we cannot take frequency too low is that in real conditions, fight conditions, the contact of our shocker to the object's body cannot be in a range of seconds. Yes, it is only maybe a part of second or half of second. And during this period, a few pulses should run through the body to have some effect. So the frequency cannot be 1 Hz of 2 Hz, for example. It should be 10 Hz, and then in real models it begins from maybe 20 Hz. Yes, and very high frequency are also inconsistent because they produce only heat in human body, and they are also used in some medical purposes. That's what about the frequency. And what's about pulse duration? Here is a picture of schematic picture of nerve in human body. The nerve is contains high concentration of sodium ions inside it, and the outer media contains a higher concentration of potassium ions. To feel pain or to experience seizures, some electrochemical process must take place, interchange of these ions inside the body, and the time constant of this electrochemical process is about 200 microseconds. This picture confirms this conclusion. This is the threshold of activation of motor neurons as a function of the pulse duration. You can see that the narrow pulses require much more current. Okay, that is the duration of the pulses should be on order of 100 microseconds or more. While for the most pronounced effect, the current should be unidirectional to this electrochemical process to be finished. Let's make some math, make some calculations. Let we have a pulse train of duration tau and period t. Mean power is given by such an expression. Here is tau and here is mean current. You can know that mean current is proportional to the voltage in the first power, and mean power is proportional to the voltage to the square of the voltage. So taking resistance of 1 kilo ohm, voltage 50 kilovolt, this is standard values, and t of about 1/100th of second. It means we have 100 Hz frequency. Power of 3 watts. It's maximum allowable from the GOST, from the standard. We obtain tau of only 12 nanoseconds permissible, and mean current of only 60 microamperes. It's too little. Our object will not sense this current. Okay, what's the problem? In fact, the pulse is also always longer due to the inductors and capacitance of our shocker and the object of application in the first. The second, in the initial moment, the resistance of the object is determined by the electrical layers, air, clothing, which we talked about, and it is much greater than 1 kilo ohm. And after breakdown, it drops sharply, as does the voltage at the output of our shocker. And the third moment is it is more correct to count the power on live tissue rather than on passive layers, i.e. the energy going to the breakdown of external dielectrics is not taken into account. Okay, let's now imagine another pulses which have such a flat part in it of much lower amplitude. For example, if we have this amplitude of this flat part U2 of 500 volts, then we get tau 2 of about 120 microseconds, much better, and mean current of 6 milliampere. It's something already. Besides, the process in most cases has an oscillatory character with a decay constant of order of tens of microseconds. This is the examples of real pulses from shockers. This is from Tazer. I don't remember. As far as I remember, it is from T Tazer, and it's from M26 model. And special methods of widening the pulse are used in them. And we will talk about this in the next part of our video. Okay, let's go to conclusions, because our video is too long already. For reliable impact on the object, electroshockers must provide an average output current on order of units or tens of milliamperes, and the peak voltage of order of several tens of kilovolts. These parameters, following to the requirements of standards, safety and portability, can only be provided when generating output signals in the form of sequence of pulses with a frequency of several tens to several hundred Hz and duration order of units or tens of microseconds. Better to have hundreds of microseconds, as we saw. Special methods of widening of output signals can be used to increase the efficiency of our shockers. Okay, in the next part we will examine the construction and schemes of really produced shockers. And that's all for today. Goodbye. It was Eugen with you.